Consider the following two problems. Suppose that we have a graph that shows the number of widgets produced, and we have profit. And we want to know right here, what is the maximum profit that we can get? So in other words, how many widgets should we produce so that we have a maximum profit? Okay, that's one problem we're going to consider. Here's another one. Suppose we have the surface area of a can as a function of the radius of the can, and we want to know what radius will produce the smallest surface area. In other words, we want to minimize the surface area. Well, both of these problems involve maximizing or minimizing something, and this is something that calculus can help us to solve. So let's look at the function f of x equals x squared. And the domain will be all real numbers. So here's a graph of this. This is just the regular old parabola that you've seen a million times before. And we notice that this has a minimum at x equals 0, right down here at the bottom. And we also notice that there is no maximum. Since the domain is all real numbers, we know that this keeps going up and up and up forever and ever and ever on both sides, and there's never a maximum value because it just keeps going. Now consider f of x equals x cubed. So again, the domain will be all real numbers, and we get a graph that looks like this. And we see that there's no minimum and no maximum. No minimum because it just keeps going down, 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 down forever and ever. And no maximum because over here it goes up and up and up forever and ever and ever. And since we're talking about all real numbers for our domain, there's no minimum and there's no maximum. Now how about the function f of x equals 2x cubed minus 2x squared minus 3x plus 1. And again, the domain will be all real numbers. So here's the graph, and we can see that minimum, well, there's no minimum overall because the graph just keeps going down, down, down over here forever and ever and ever. But what about this place right here? That kind of looks like a minimum nearby. So maybe we might say that there's a minimum at this x value right here, but I don't know, maybe not. And what about maximum? Same deal. Over on this side, it goes up and up and up forever and ever and ever, but this over here kind of looks like a maximum. And so maybe we might say that there's a maximum at this x value here. But again, we don't know for sure. So we need some definitions to kind of sort this out. So let's define a function with a domain D, and we'll look at absolute maximum first. So the function f has an absolute maximum, or some people call it a global maximum, at a if f of a is greater than or equal to f of x for all x that are in the domain D. And that value, f of a, we call that the maximum value of f on the domain D. And then the absolute minimum works kind of the same way. The function f has an absolute minimum, or some people say a global minimum, at a if f of a is less than or equal to f of x for all x in the domain D. And again, the minimum value of f on the domain D is called f of a. Now what about the things that we saw on the last graph that weren't maxima or minima overall, but they kind of looked like maxima and minima nearby? Well, these are local max and local min. So a local maximum, the function f has a local maximum, or some people say a relative maximum, at a if f of a is greater than or equal to f of x for all x in some open interval containing a. That just means nearby a, it looks like a maximum. And a local minimum, similar definition, the function f has a local minimum or a relative minimum at a if f of a is less than or equal to f of x for all x in some open interval containing a. Okay, so let's look at an example. F of x equals 3x to the fourth plus 2x cubed minus 3x squared minus 2x plus 2, and the domain will be all real numbers. So here's the graph, and we'll first look at absolute maximum. So if we look for an absolute maximum, well, we see that the graph keeps going up forever and ever and ever on both ends here, so we could say that there aren't any, or there isn't an absolute maximum here. So I'm just saying none. We don't have one. Okay, next we'll look at absolute minimum. This I think we do have, because if you look down here, this is the lowest point on the graph. So this right here would be an absolute minimum. And so this is the x value of that absolute minimum. And so this absolute minimum happens at x equals about 0.65. So I'll write that here, x equals 0.65. That gives us the x value. And then if I wanted to find the value, the minimum value, that would be this value on the y-axis. I could do f of x, or f of 0.65. And if you plug that in, you can use a calculator to get the value here. That ends up being 0.52. So we could say that f of x has an absolute minimum at x equal to 0.65, and the minimum value is 0.52. How about a local maximum? So we saw that there was no absolute maximum, but there does appear to be right here something that looks like a local maximum. Nearby it looks like a maximum. And so the value, the x value, would be this value right here. And that looks to be x equal to negative 0.30. So you might not know how I'm getting these numbers yet, and that's okay. You'll find out pretty soon. But for now, we're just trying to identify them. And to find the value, we can do f of negative 0.30. And you can plug that into a calculator if you want, and you end up getting 2.30. Okay, and so that, let's just check and see, 2.3, yeah, that looks about right. Okay, and that seems to be the only local maximum. How about local minimum? So for a local minimum, we have this right here. This does look like a local minimum. It's also an absolute minimum, but it still counts. So we have x equaling 0.65, and we saw earlier that f of 0.65 was 0.52. Okay, so that's a local minimum. Are there any others? How about this right here? This seems to be a local minimum, so we want this x value right here. And for that local minimum, that x value is negative 0.86. And then we can find the actual value here in f of negative 0.86, and that's about 1.87. Now let's just check 1.87. Yeah, that seems to be about right. Okay, let's look at another example. So let's take that same function that we had before, except now let's restrict the domain to be between negative 1 and a half, and we're going to include negative 1 and a half in the domain. So now we get a graph that looks like this. So we just have the graph between negative 1 and a half. And that's negative 1 on the x-axis and a half on the x-axis right here. So we kind of chopped off the other parts of the graph here. Absolute maximum. So before, if you remember, we did not have an absolute maximum. But now all of a sudden we do have an absolute maximum, and that's going to be this value right here. This is the highest point that the graph reaches, so I can draw this down here, and the x value would be the location of the absolute maximum, and that's at negative 0.30. We saw that before in the previous slide. And f of negative 0.30, if you were to figure that out, it's 2.3. And that looks to be about right. How about an absolute minimum? Well, we do have an absolute minimum, and this time it's right here. That's where the function reaches its lowest point, and that happens right at the end of the interval. That's at x equals a half. And so if we look at f of a half, and I guess I'll write this as a decimal here, that's 0.69, and that looks to be about right. Okay, how about a local maximum? Well, the local maximum is the same as the absolute maximum here. This is the maximum right here, and that's the only one that we have. So I'll just copy this down again. We have a local maximum at negative 0.3, and f of negative 0.3 was 2.30. Okay, how about a local minimum? Well, this right here is an absolute minimum, but it doesn't count as a local minimum because it's not a minimum nearby. But this over here does. This right here, that's going to be our local minimum. And so that happens at x equals negative 0.86. And f of negative 0.86, And if you plug that into a calculator, you get 1.87. Okay, let's look at another example. Okay, how about f of x equals x sine x, and the domain will be -3 to 3, and we're going to include -3 and 3. Here's the graph, and we want to look first for an absolute maximum, and we see that the absolute maximum happens in two different places. It's the same value here at the top, so we have an absolute maximum here, and I'll bring that down here, and we have an absolute maximum here. I'll bring that down here. Okay, so we have two of them. We have an absolute maximum at x equals -2.03, and we have an absolute maximum at x equals +2.03. And so the value at each of these should be the same, so f at -2.03 should equal f at +2.03. They're the same maximum value. And if you check that, you get 1.82. And that seems to be about right, 1.82. And that's the absolute maximum. The absolute minimum, well, there's just one of those. This is the lowest that the graph gets down here. And so that's right at x equals 0, and you can see that f of 0 is 0. Okay, how about a local maximum? Well, for the local maximum, again, we have these two peaks right here. And so again, we have the same thing that we had for the absolute. We have -2.03 and +2.03, and we see that the value of the function is the same at each of these. So f of -2.03 is the same as f of +2.03, and that's equal to 1.82. And how about a local minimum? Well, the local minimum, again, is the same as the absolute minimum. So that's x equals 0, and f of 0 equals 0, and that's because this is the lowest that the graph gets. Okay, how about f of x equals x plus the natural log of x minus 1? And the domain will be 1 to infinity, and we're not going to include 1. So this is the graph, and you can see why we didn't include 1. There's an asymptote there. And we want to look for an absolute maximum. Well, the graph keeps going off forever and ever and ever. The domain goes off to infinity. So, nope, we don't have one. How about an absolute minimum? Well, if we go the other direction, it goes down, down, down forever and ever and ever. Nope, we don't have one of those either. All right. How about a local maximum? Well, there's no place on here that I see that looks like a maximum. Nope, we don't have any of those. How about a local minimum? Again, nope, nothing there. So in this case, we don't have any absolute or local maxima or minima. Now, what would happen if I took that same graph, but I restricted the domain to go from 1 to 4, and we're not going to include 1 and 4? So the 1 is where the asymptote was, but now at 4 we have an open circle. 4 is not included in the domain. Absolute maximum. Well, you might be tempted to say that there's a maximum right here, but think about it. 4 can't be a maximum because 4 is not in the domain. Well, maybe something right before 4, like 3.9. But then what about 3.99 or 3.999 or 3.99999? And it just keeps going, and you can see that there is actually no maximum here. So again, nope, we don't have one of those. How about an absolute minimum? Well, we saw before that this keeps going down here forever and ever and ever, so nope, none of those. How about a local maximum? Well, again, we have that same problem here. That doesn't count. There's no other place for a maximum, so again, nope, none of those. And how about a local minimum? And again, oh, we saw this before. Nope, none of those. So in this case, even after we restricted the domain, we saw that we still do not have an absolute maximum or minimum, and we don't have a local maximum or minimum. Now, if I had changed the domain so that this was not an open interval here, but a closed interval at the end, if I filled in that circle and included the 4, then all of a sudden I would have an absolute maximum, because then 4 would be my absolute maximum. But as it stands here, nope, I do not have one.